Hey there, chemists. In this lesson, we're going to look at different melting points and boiling points of various substances and qualitatively talk about how we can rank the different types of interparticle attractions or forces of attraction that simply cause molecules to stick to each other and give them different melting points and boiling points. To kick us off, I've got a demonstration, really just a thought experiment for today. Think about these common household things: aluminum, glycerol, glass, graphite, wax, olive oil, and salt. And ask yourself, which one do you think has the highest melting point and which one has the lowest? And then check back and see how you did. Okay, so let's start with the highest one first. That's going to be graphite. If you guessed graphite, you are indeed correct. Graphite melts at about 3,600 degrees Celsius. It is a network covalent solid. It's one of the allotropes of carbon, and we'll talk in a moment about why it has such a notoriously high melting point, higher than anything else up there. If you're going down from that ranking and you're trying to find the ones that are next, after graphite, we would hit the glass right next to it. That's at about 2,000 Celsius. And then we'll just keep going in that direction from high to low. Below the glass, we get to salt way over on the end. That's about 800 Celsius. And below that, we get to the aluminum metal. That's about 600 Celsius. And then we work our way into covalent compounds. So things like glycerol, much lower melting, about 20 Celsius. Glycerol is a liquid, but it freezes at 20 degrees Celsius if you're going in that direction, and it melts if you're going from solid to liquid at 20 degrees Celsius. I actually skipped one, didn't I? Wax is a little bit higher melting than that. Wax is obviously a solid, but it's a pretty low melting solid. It's 40 Celsius, roughly. And then olive oil is the lowest one. This is below 0 Celsius. It's about -6 before you can get liquid olive oil to freeze into solid olive oil. So why is this? Why do these two in the middle have such high melting points in the thousands, but things like aluminum and salt are in the hundreds, and then things like glycerol, wax, and olive oil are down in the tens and even the negatives for things like melting point? Well, it has to do with just what type of substance they are. And there's 4 main categories that we can use to describe essentially every single substance out there, starting with network covalent solids. There are 3 network covalent solids that you should know, namely the one that's up above, graphite, and then the other allotrope of carbon, diamond, and silica. There are many more than just those 3, but you should definitely know those 3, just for starters. And let's talk melting point. The melting point of graphite, well, we have it up above. It's about 3,600 Celsius. Diamond is a little bit more. It's hard to get an accurate, or I should say precise number for this, but I've seen 3,700. I've seen up to 4,000, depending on what pressure you're at, obviously, but a little bit higher than graphite, but they're very similar as allotropes of carbon, and both being network covalent solids. Silica, which is quartz, the crystalline form of glass, melts at about 1,700 Celsius. And the reason these are all so high melting is because the structure looks something like this. It is a network of covalent bonds. And as such, when you melt something, you're actually breaking covalent bonds when you melt it. So covalent bonds break during melting. That's never true for other substances. When you melt something, you break intermolecular forces, or you get ions to move farther apart from each other in ionic solids, what we'll talk about next. But in covalent substances that are network covalent substances, you actually break covalent bonds during melting, and that's a big deal. So these are very, very high melting because you're actually breaking apart these covalent bonds, which are among the strongest bonds out there. And that's why it takes so much temperature, so much heat to melt something like graphite or quartz. Well, what about the next batch of substances, the ionic solids, things like sodium chloride, which we saw melts at about 800. Celsius. So it's not as high melting as network covalence, but ionic bonds are very strong in the solid state because they exist as a lattice of cations and anions. And within the ionic substances, we can actually talk about what makes them have stronger ionic forces. For example, if I compare sodium chloride with magnesium oxide actually has a much higher melting point. It's about 2800 Celsius. It's borderline as high as some of the network covalents. So these rankings are not absolute, by the way. There's definitely some gray area of overlap in between. However, within the ionic compounds, we can rank why something like magnesium oxide has such stronger forces of attraction within it than sodium chloride. And it has to do with two things. Number one, the greater the charge, and number two, the smaller the ion. You put those together, you get a stronger, I'll just say strong coulombic, meaning a strong coulombic force of attraction. Maybe you know from your physics class, there's an equation for Coulomb's law for charged particles. It says that the force of attraction is a constant times the product of two charges divided by the distance that separates them squared. So if they are close together, and if they have big charges, then you have a strong force of attraction, a strong coulombic force of attraction. So if you compare magnesium oxide versus sodium chloride, think about the charges in magnesium oxide. It's 2 plus and 2 minus, isn't it? So that's bigger than, let's say, +1 and -1. So we have greater charge magnitude, which is usually the more significant thing when you're talking about coulombic forces of attraction for ionic solids, because you double the magnitude of each one in this case. The magnesium ion also is fairly small, and oxide is fairly small too when you compare it with things like chloride. So both of those actually work. It's both bigger in charge and smaller in ionic radius, therefore closer together. You could think about what it is just to make these bonds between the two atoms as long as they are closer to each other. That's true if the ions are actually smaller. So the separation between the two is smaller, giving it a stronger force. So those are the two higher melting categories, the network covalents and the ionics. After that, we get to some lower melting ones like metallic solids. Metallic solids are different in structure, as the picture down here shows. Here we have a sea of electrons surrounding positive nuclei. And this is what a solid metal looks like. All the different positively charged nuclei of the metallic atoms share this cloud of electrons between them all at the same time. That's why they conduct so well, because those electrons are mobile, so they conduct electricity and heat very well because of that. It's also why they're quite malleable. You can bend and stretch and everything is still in contact with that sea of electrons. Unlike ionic substances, which if I try to break an ionic substance, they're not malleable, they're very brittle. They snap in half, and that's because if you shear a layer of ions, you would end up getting two like charges to be right on top of each other, and they would instantly repel. And you'd actually get a whole layer of ions to repel each other. All these pluses and minuses would not be alternating anymore. They would be lined up, and then you would break apart. Hence why ionic salts are brittle, and metallic solids are quite malleable. Now, what about trends within the metals? It's hard to get a perfect trend of melting points, but I'll show you a couple of examples. Lithium has a melting point of about 200 Celsius, whereas sodium melts at about 100 Celsius. And for the most part, a smaller radius equals a higher melting point. They can just stick together more strongly. So those are the first three, and now we're going to talk a lot about the last one. Most of this lesson is actually all about this last category, molecular solids. Molecular solids are discrete meaning individual covalent particles. So here's a bunch of phosphorus molecules of P4. Remember, phosphorus is a tetraatomic substance. So it's these little clusters of molecules of phosphorus. And what gives molecular solids higher forces of attraction is all based on their intermolecular forces, or IMFs. So wax, which melts at 65, versus glycerol, which melts at 20. It turns out that wax has stronger intermolecular forces. So we need to answer, what are the intermolecular forces? How do we identify what they are? And how do we know when some of them are stronger, or can we predict when they're stronger? And that's what the next section is. So this entire section here is specifically related to molecular solids. These are only for molecular compounds. There are three types of intermolecular forces that molecules can exhibit. The first one is called dispersion forces. Dispersion forces are induced dipoles. Molecules have electrons, and the electrons can be polarized. And if you have a larger molecule, what that means is you have more electrons, and that means you have more polarizable electrons. They can actually distribute themselves throughout the molecule and separate. So if I look at an example, here's some methane molecules, and here's some silane molecules, SiH4. And if I compare the boiling points of each of these, they're both very low boiling. Methane boils at 162 Celsius, but silane boils up at -112. Silane has a higher boiling point. These are both non-polar, very lightweight molecules, but silane is bigger. It has more electrons, and those electrons can polarize. So they can give it this partial negative and partial positive character once it lines up with other molecules of itself. It will do that to give what looks like a partial negative and a partial positive charge on each side of the molecule. And it just does it better than smaller molecules simply because there's more electrons to do that. So silane molecules stick to each other more than methane molecules. Dispersion forces are among the most significant force because everybody has them, and you can get molecules that are really big. Hence, they have really high melting and boiling points as a result. That's actually why wax was the highest one, because wax, or at least the highest of all the molecular substances between glycerol, wax, and olive oil, wax was the biggest one, and it only has dispersion forces, but it's made of these big, long, zigzaggedy hydrocarbon chains, and they stick to each other really well in layers because they have such strong dispersion forces, just because it's a big molecule. Okay, but there are other forces to talk about. The second type of force is called a dipole force. This is from an existing dipole in polar molecules. And as long as you are a more polar molecule, you have stronger forces. That's it. So for example, silane, just to use it again, which we already know is -112, and silane is nonpolar. It's got a symmetric distribution of charge. Those 4 hydrogens are tetrahedrally arranged around each silicon atom, so there's no pre-existing dipole. But right next to it, molecules of hydrogen chloride, HCl, has pre-existing dipoles. So it boils at a higher temperature. It's about 85 below zero. So HCl has stronger forces of attraction based on the higher boiling point. I wouldn't necessarily predict that, but you could safely guess it because it's polar and silane is nonpolar, and they weigh roughly the same. HCl is 36.5. Silane weighs about 32 grams per mole, which is correlated with how many electrons it has. The bigger you are, the more electrons you have, because we're not just talking valence, we're talking all the electrons in those molecules. Okay, lastly, the intermolecular force you probably remember the most from your intro chemistry class is H bonding. H bonding is a special IMF between, as it sounds, an H and a lone pair on N, O, or F. Specifically, the three smallest, most electronegative elements on the table. And it's just to remind you what we see between molecules. All of these intermolecular forces are between molecules. So there's an H bond between two molecules of HF. Here's an H bond between two molecules of water. Here's another H bond between two molecules of water. It's always between two separate molecules that we get the intermolecular force. And any lone pair can do it as long as it's on an oxygen or a nitrogen or a fluorine. That's because they're the most electronegative and smallest, capable of forming covalent bonds. And the H can do it as long as it's directly attached to a nitrogen, oxygen, or fluorine with at least one lone pair. So HF can do it, water can do it, ammonia can do it because it's got the lone pair on the nitrogen and an H directly attached to it. And other molecules that are even bigger can certainly H bond as well. Here's the acetic acid molecule with two hydrogen bonds connecting two water molecules. So sometimes you can make multiple H bonds. And just to continue with what we were doing and comparing temperatures of melting points, HF happens to boil at 20 Celsius. Water, as you all know, boils at 100 Celsius. So comparing these molecules, HF weighs about 20 grams per mole and water weighs about 18, so similar dispersion forces. They're both polar. It's hard to rank polarity without being given a lot of information. They're also both capable of H bonding, so it might be a question as to how come water is has such a high boiling point. Well, water is a perfect H bonder because there's a 1-to-1 ratio of hydrogen and lone pairs. I'll make a note of that down here actually because we're going to comment on that right here. Water is a perfect H bonder because of that 1-to-1 ratio of H, and I'll just draw a pair of dots, meaning a lone pair. So if I have a cluster of water molecules, I can H bond between all of these, I'll draw them as dotted lines, between all of these hydrogens and lone pairs, and every single lone pair will get to participate in an H bond with someone else's hydrogen. Likewise, everybody's hydrogen gets to participate in an H bond with another water molecule's lone pair. And this just continues even into other molecules that aren't drawn in this giant network. This is what you would see in, let's say, just a crystal of ice. You would have a continuum of H bonds, very strong intermolecular forces between water molecules. Okay, so for the rest of this lesson, let's just look at some examples of molecules and specifically comment on what makes sense based on the given data. Starting with these three. Below each structure, what's the most significant IMFs you would expect to see? And then can we rationalize what we see about things like the boiling point, the physical properties? Well, water has dispersion forces because everybody has them. That means ethanol has dispersion forces, and ethyl ether also has dispersion forces. Water is polar, so it has dipole forces. Ethanol is also polar, so it also has dipole forces. And ethyl ether is also polar. Don't let that linear-looking molecule fool you. This is a bent oxygen in the middle of it, just like it's a bent oxygen in water. They just drew it linearly, but it is a polar molecule. Water can H bond, and ethanol can H bond as well. As you can see, there's an oxygen with a lone pair and a hydrogen on it, so that is the key feature that lets me H bond. Now, ethyl ether cannot. It's got lone pairs and an oxygen, but there's no hydrogen directly attached to the oxygen, so there's no H bonding found in an ethyl ether molecule, so that doesn't exist. So that might be enough to explain why the boiling point of ethyl ether is the lowest. That also is shown in this picture right here. It's the easiest to vaporize. So I have the highest vapor pressure, highest P vape. We're going to talk about vapor pressure in the next lesson, but it's worth just mentioning here. Vapor pressure is simply the amount of vapor, gaseous forms of that substance in equilibrium with the liquid at a given temperature. It only changes with what temperature you have and what the substance is. And at a given temperature, ethyl ether has the weakest IMFs, so it's the easiest to boil and therefore the easiest to vaporize. So it would have the most amount of vapor in an equilibrium mixture. What about the other two? It looks like water boils at a higher temperature than ethyl alcohol, even though they both have all three of these IMFs. Well, and I would argue the ethyl alcohol molecule has stronger dispersion forces than water because there are more electrons, but that's not enough to outweigh the perfect H bonding ability of water. Water still only boils at 100. Don't think that all of a sudden it's the highest boiling or melting covalent substance in the world. There's plenty of things that are higher melting or higher boiling and they don't have H bonding. They just happen to be bigger molecules. So speaking of, let's wrap up by looking at a lot of different molecular substances and trying to identify what IMFs you would expect for them to have, and then we'll pick two and comment on the ranking. First, hit pause and draw a structure, just an abbreviated structure for each of these covalent compounds. Remind yourself how bonding works, and then come back and see how you did. Okay, so let's look at those structures. Ammonia looks like that. Carbon tetrachloride. I'm not going to draw all the lone pairs because you should know they're on every chlorine atom. Likewise with the fluorines in trig planar boron trifluoride. Likewise with the chlorines in chloroform. Likewise with the chlorines in phosphorus pentachloride. There's your trig bipyramidal. Carbon dioxide. Yeah, I'll put a couple lone pairs in just to remind you that they're there. Sulfur hexafluoride. There's lone pairs on all those fluorine atoms. And then methanol. This is the methanol molecule. If you forgot that name, that is a combination of a tetrahedral carbon and a bent oxygen. Okay, so what IMFs do we think these molecules will have? Well, everybody's got dispersion. Everybody's got dispersion. So I'll go ahead and write it. Dispersion, dispersion, disp, disp. Go ahead and write them down. They all have it because they're all molecules, which means they have electrons that are capable of polarizing and creating induced dipoles. What about dipole forces? Well, ammonia is polar, so it has dipole forces. Carbon tetrachloride? Nope, nonpolar. Boron trifluoride? No, trig planar, nonpolar. Chloroform is polar. That has dipole forces. That's asymmetric. Even though it's tetrahedral, the three chlorines aren't the same as the one hydrogen, so it's asymmetric. Phosphorus pentachloride, nonpolar. CO2, nonpolar. Sulfur hexafluoride, nonpolar. Methanol, that's polar. Dipole forces. And then what about H bonding? H bonding, ammonia can do it, so H bonder, yes. Carbon tet, no. Boron trifluoride, no. CHCl3, no, no, no. Nothing else can H bond but methanol. Methanol can H bond. So you should be okay with coming up with what forces a molecule has. And now we can actually talk about the strengths, the relative strengths of those forces. But you got to be given the data to really do this. It's really hard to predict. For example, let's just look at the first two. Let's consider ammonia, which is negative 33, versus carbon tetrachloride 77. 77 is a much higher number. But carbon tet has only dispersion forces? Yes, the dispersion forces are very strong in carbon tetrachloride because it's a big molecule. Each of those chlorines has a lot of electrons, not just the valence, but all the electrons in the inner core are polarizable as well. Ammonia is a tiny little molecule, and even though it can H bond, that's not enough to overcome the comparable forces that carbon tetrachloride has. So we could end with just a short sentence that says, let me make a little space here, that says CCl4, I'll write it a little bit smaller, CCl4 has a higher boiling point, BP, than NH3 because its dispersion forces, its disp forces, are stronger than NH3's combined forces. I really want to get that word combined in there, so I'm going to move this up a little bit up here. Then NH3's combined dispersion, dipole, H-bond forces. That's a little lengthy and almost repetitive, but it's the kind of thing that the AP would expect a student to write as an argument. So I'm even going to put a box around that. If you didn't fit it completely in your notes, that's okay, as long as it makes sense as you're looking at it. Carbon tetrachloride has a higher boiling point. True, it was given, because its dispersion forces are stronger than the combined dispersion, dipole, and H-bonding forces in ammonia. This is a classic thing that the AP does all the time. They'll give students an example of something that has H-bonding, and many people incorrectly think that that automatically makes it a more tightly held together molecule in terms of its IMFs. Not always true, because dispersion forces can be big. Okay, so that was meant to go over a lot of detail about intermolecular forces and how to use them to rank given pieces of information like physical properties, primarily boiling points and melting points, and even a little bit with vapor pressure. And outside of intermolecular forces, we can talk about the other three types of substances as well, metallics, network covalents, and ionic compounds, to group any cluster of substances into these categories and talk about their forces of attraction.